share your screen if you want.
All right. Well, welcome everybody. Thanks for joining this session. It's going to be just some fun, like, you know, elementary math. And there's absolutely nothing new here, and that's by design. That's the great thing of a conference like Rebase. There's no reviewer too, so we can just like, you know, like have fun with stuff that we like. I don't know about you guys, but I'm having, like, you know, during COVID, having like lots of dreams, like every night, like, you know, crazy dreams. And a lot of these dreams are actually about that I skipped math classes. It's actually so bad that sometimes I have to really check in the morning, like, yes, I did really graduate. But yeah, it's super crazy. And it's got especially crazy because a while back, I kind of predicted that Software 2.0 would be the combination of probabilistic and differentiable programming. And those two kinds of programming are very kind of calculus heavy. If you look at differentiable programming, well, obviously that's about differentiation. Why is it about differentiation? Well, if you want to get, like, you know, take the derivative of a program is composed out of smaller pieces, maybe functions, and then you can use the chain rule to like compute the derivative of the whole program. If we double click on what the derivative is, we get this like standard definition in terms of limits. A function is differentiable if this limit exists. And then if we double click on limits, we get to the dreaded epsilon delta definition of limits. I'm sure that, like, you know, that is the reason that I have so little hair today. If we look at probabilistic programming, that's all about integration. Maybe that's a little bit more surprising, but let's look at kind of like, you know, probabilistic programming. Probabilistic programming is really programming using the probability monad. And if you look at the implementation of the bind of the probability monad, that uses integration. Now I know that monads are getting out of fashion. I'm old-fashioned, but like people now want to do algebraic effects or I don't know what. So even if you don't like monads anymore, here's another reason why you need integrals when you're doing probabilistic programming. Because when you have a probability density, in order to turn that into a probability, you have to take the integral over a particular range. Because if you take the density at a certain, the probability for a single point is always 0. So you have to get, like, you know, take an integral over a certain fragment of the curve. So what is an integral? Well, integral is defined as the area under the curve. And then let's zoom into that. And there, oh my gosh, we see again things with limits, with epsilons and deltas. And like, you know, more hair loss will be the result here. So the question is, if we're moving from software 1.0 to software 2.0, where we move from the discrete world to the continuous world, where we move from exact results to probabilistic results, do we also have to move from algebra to calculus? Which means that all of us have to retrain, because traditionally all our programming theory is based on algebra, and suddenly we have to kind of change. And I don't kind of like that. I really like algebra. So can we kind of like save this? And the story that I'm going to tell you today is we don't have to worry, everything will be all right. We don't need calculus, we can turn everything into algebra. And the reason is that if you look at real numbers, they're just another algebraic data type. It took the mathematicians like hundreds of years to come up with a definition of the real numbers. I mean, people tried for a long time, and then Cantor, I think this is the definition that we currently use, defined the real numbers using these rules or axioms, but that's definitely not the only way you can define real numbers. So here's another version of real numbers. I'll call them the lover real numbers, and they are defined using a number of axioms. And also notice the subtle difference. I'll use the double struct R for the traditional real numbers, and then the just a regular or bold-faced R for these lover real numbers. And one thing to note here is you can ignore axiom 1 and 2. It really axiom 4 is the important one. Is it says that there is a subset of these numbers for which the square equals 0, and then for each function from that subset to R, there is a unique A such that f of d equals f0 plus d times A. So axiom 4 is really the crux here. So let's look at this in some detail again, but I want to really put this piece of notation in your minds. The Cantor's reals are double struct, and the lover's reals are just R. And this, these two systems are incompatible. So if we assume that we have the standard real numbers, the Cantor real numbers, and we can look at the set of values d such that d squared equals 0, then that is that's the set with just the value 0. And then if we look at the function that just maps at the constant function 0, then we can prove here. I won't go to the proof in detail, just just scan it here. But we can prove now that 0 equals 1 if we assume axiom 4. So axiom 4 is not valid or is not compatible with the standard real numbers, and vice versa. If we assume that we do have a set of nilpotent infinitesimals, that's how these things are called. They are infinitesimals. They're super small, and if we take the square, they become 0. But if we now define a function using case distinction, using a conditional, then we can also show that 1 equals 0. So we get another contradiction. So what we have shown here is that Cantor's reals are incompatible with nilpotent infinitesimals, and lover's reals are incompatible with case selection. And now chaos is there. In order to deal with the lover's reals, we have to move to Topos theory and to intuitionistic logic, and it's just super complicated. And today I just don't want to go into that rabbit hole. So what we'll do instead, we'll do something much more simple. All right, so we're not going to deal with lover's reals for now. We're going to simplify things, and we get 80% of what we want with 20% of the effort. And it's a little bit like studying fruit flies in order to understand dolphins. By studying dual numbers, we will understand this kind of complicated synthetic gradient, synthetic differential geometry. So here I made a typo here. It's too much deep learning here, but we're studying something simpler to better understand something more complicated. So what are dual numbers? Well, dual numbers are pairs of real numbers where the second part of this pair is an infinitesimal. So it's like a plus a epsilon, where epsilon squared equals 0. And now the beautiful thing here is that something similar to axiom 4 holds here, namely that if we lift a function from the real numbers to dual numbers, it computes the original value of the function and its derivative. So it returns a unique dual number that represents the value of the original function plus its derivative. And again, you see here, just like in axiom 4, that is like, there's this uniqueness aspect, and that will be kind of super critical for what we're doing in the rest of this talk. Now, what's interesting here is that if I multiply two numbers like a epsilon times b epsilon, that becomes 0. So really, one way to look at epsilon is not as a value by itself, but as a unit of perturbation. It's like a unit of measure. So epsilon is the unit of perturbation, and later we will see that we will need multiple units of perturbation because we can get perturbation confusion, and so we have to kind of distinguish different perturbations. What we'll do here is we will define, just like before where we defined this set D of nil squared infinitesimals, we will define this set epsilon, we'll call it here epsilon, which is all the values, all the dual numbers where the real part is 0. And when, when we square the like infinitesimal part, that will become 0 as well. So like epsilon is the subset of like nilpotent infinitesimals of the dual numbers. So that's another type that we will use in what follows. All right, now how do we prove that this dual numbers property holds? Well, easy. We just apply Taylor expansion. You go to Wikipedia, you look for Taylor expansion, you instantiate the theorem, and then lo and behold, you can prove that f of a plus a epsilon equals f of a plus f prime a epsilon. Now, this is kind of like a little bit dodgy because it kind of assumes that we already know what derivatives are. And the whole point of this talk is to try to understand what derivatives are. And moreover, it kind of like, if you look at the second line here, it does arithmetic with dual numbers, which we haven't defined yet. So think of this just as an intuition why this dual number property makes sense, but this is not valid as a proof. This is just kind of like, completely wrong. So we just use this as an intuition pump, but we cannot use this as a proof. Let's try another thing. We defined derivatives using limits. Limits, well, this h goes to 0, that's a really tiny value, so why not just replace the limit by this infinitesimal thing? So we will just define the derivative as the same term up there, except that instead of the limit goes to 0, we replace h by a epsilon. Well, that's not valid, because if you can divide by epsilon, then you can prove that 0 equals epsilon, and that's something now everything collapses, right? Because we assumed that epsilon was not 0, epsilon squared equals 0, and so we are kind of like lost again. So we cannot divide by epsilon, but we don't need to divide by epsilon. We can just use structural equality. So if we look at two dual numbers, a plus a epsilon equals b plus b epsilon, then those two are the same if a equals b and capital A equals B. And if we just drop the first part, we can say that A epsilon equals B epsilon if and only if A equals B. So that's all we need. And so we don't need to use division by epsilon. We can just use this thing which is called micro-cancellation. If we can prove that A epsilon equals B epsilon, we can drop the epsilons and conclude that A equals B. Now, let's do a proof here. So we can prove here that using a micro-cancellation that f of epsilon equals f of 0. But then we can kind of like, does that mean that we can like, that epsilon equals 0? Well, this is not really true because we are using micro-cancellation here, not on dual numbers, but on if you look at the first thing here, this is not kind of like, f of epsilon is a dual number and we're multiplying it here by epsilon. So really this is like, f of epsilon times 0 plus 1 epsilon. So we're really not using micro-cancellation here. So this like thing here is like wrong. But we can use micro-cancellation for real. For example, we can prove very easily, it's maybe a little bit complex here, that the derivative of the inverse of a function is 1 divided by the derivative applied to the inverse of the function. And you can see here that this thing requires no limits. It just is standard algebraic reasoning. We can also just derive the sum rule, the product rule, the quotient rules, all follow from just simple calculation. We don't need to have any kind of notion of limits, no epsilon deltas. Well, there's epsilons, but these are very different epsilons. It just is easy calculation, and you see here that we're using the fact that epsilon squared equals 0 for the product rule, but we don't even need that for the sum and the quotient rules. We can also use or compute the derivatives for sine, cosine, and tangents. And for that, we need to first kind of understand what the sign of epsilon is. And for that, we can use some really, really old math from the 1400s. But once we have convinced ourselves that the sine of epsilon equals epsilon, the cosine of epsilon equals 1, now we can compute using micro-cancellation that the derivative of sine equals cosine and the derivative of cosine equals minus sine. And just look here at the calculations. You don't have to follow every step, just look at them and you see that it's really all the steps are very simple. You're using either properties of dual numbers or standard properties of sine and cosine and simple arithmetic. And of course, our assumption that cosine of epsilon equals 1 and sine of epsilon equals epsilon. But you see that we have really achieved our goal of turning calculus into algebra, because all these calculations are purely symbol pushing, and that's what I like. Now, the nice thing about dual numbers is that you can easily translate them into code. Just take the rules that we just had in math, transliterate them into code. I'm using Kotlin here, and you have an implementation of automatic differentiation. This is forward, known as forward automatic differentiation. Backwards automatic differentiation, that's the one that's used mostly by deep learning frameworks, is basically continuation passing transformation applied to forwards AD. There's a little few tweaks. You have to be careful with sharing in your expressions, but that's not too difficult. It's still basically a continuation passing style applied to forward AD. And there's many papers, people that talk about this. And so we won't touch that in this talk. All right, so now that we know what dual numbers are, we get a sense of differentiation. We've seen all the rules, product rules, the derivative of sine and cosine. Now we're going to shift gears a little bit. And what we're going to do is we're going to take our original formulation of the dual numbers property, and we're going to write that into point-free style. So what we're going to do is we're going from the formulation here above in the red, and we're going to turn that into the formulation here in yellow. And what we're going to use for that is we're going to use scholemization. And scholemization is a way to eliminate existential quantification from a formula. And the way we do that is shown here in the bottom left, is we're going to take the formula, and if there's an existential quantifier after a universal quantifier, we're going to replace that existentially quantified variable by a function of the universally quantified variables. And intuitively, what it says is that, like, you know, for all x, there exists a y, such that px of y. Well, let's have a function that given x will kind of produce that witness for us, and that function will just magically find that particular y. All right, so this is columnization. It's also kind of like, you know, old math. And here are a couple of examples of using columnization for the 3 different ways people use existential quantification. So there is, like, you know, for all x, there exists at least one y. We can write that in columnized form as px, comma f of x, or we can, like, you know, move that fx out of that p with an implication. Then we have, like, you know, for all x, there exists at most one, typically written with like the accidental quantifier with a question mark. If you look at the bottom line here, we can kind of like write that in columnized form as pxy implies that y equals f of x. And then unsurprisingly, for all x, there exists exactly one y, such that pxy. That is just the conjunction of at least one and at most one. So you will see there like px comma y, if and only if y equals f of x. So this is again, like, you know, a really important transformation that will allow us to turn our original dual numbers formulation into point-free style. But before we do that, let's look at a kind of concrete example here. And if you get like look in your whatever middle school math book and look up the definition of when a function is bijective, you see that a function is bijective if for all b there exists exactly one a such that f of a equals b. If we write this in columnized form, and we get like here, we are in the 3rd column there, there's exactly one, and we've changed x's and y's and a's and b's. But if we write this in columnized form, we get f of a equals b if and only if a equals the inverse of f applied to b. And this is a way much nicer formulation, I think, than the one with the kind of complex quantifiers. It just shows like, you know, like f of a equals b if and only if a equals f inverse of b. All right, keep this formula in your mind because we will see this again later. Right, so the first step is to take our formula, the original dual numbers formula, and we're going to columnize it. So we're going to remove like the existential quantifier, and then we just get this one here, f of a plus a epsilon equals b plus b a epsilon if and only if b equals f of a and b equals f prime of a. Don't even like, you know, try to understand what this formula says. Just apply this rule mechanically. That's what we're going to do. That's what algebra is great for, right? Just apply rules mechanically. The first step now is to remove the a plus epsilon from this formula. And for that, we're introducing a function alpha. And alpha really just does take 2 parameters, and it just adds them up and multiplies it with the gap, like with the parameter. So alpha of a comma a, it takes another parameter d, and then does a plus ad. We can write that in slightly more point-free form by removing the lambda d, by writing it function composition. And if you're really a Haskell fanboy, you can write it as uncurried dollar with kind of like function composition, but we're not going to go that far. We're writing things point-free, but up to a point. If we apply this function, if we substitute this function alpha here, and we apply at a reduction, we can take this red formula and turn that into the kind of green formula below. So f of a plus a epsilon equals b plus b a epsilon becomes f compose alpha comma 1 equals alpha comma a comma b. There's a kind of like slightly sarcastic remark there. It's so much clearer. Again, don't worry about readability. What we're doing is we're mechanically transforming this formula. And once we're done, that's the point where we're going to interpret again. So for now, just mechanically translate, convert these formulas. Second step is we're going to remove this conjunction. And for that conjunction, we're going to lift function application. So we take this little triangle, takes two functions and one argument and passes the argument to the both sides of the triangle and applies the function to it. So the second line there, f triangle g of a is f of a comma g of a. You can write that completely in point-free form. I think there should be some f and g's and a's kind of like, you know, at the end there, but you can see like we won't do that kind of completely point-free. If we do that, we can eliminate the conjunction because the conjunction is really got like something that says that the pair b comma b equals f of a, f prime of a. And if we apply this function here, now we get the pair b comma b equals f triangle g applied to a. All right, and again, don't worry about like, you know, that things become more and more unreadable. We're just mechanically transforming the formula. If we now apply these transformations to both sides of the of our dual numbers property, we get the one here in yellow. And what you see here is that there's still some, like there's the b comma b appears on both sides. There's still kind of like an application to a. So we can continue to push on this and get it a little bit more concise. In order to do that, we need to lift the two functions here, the one function that takes the real part of a dual number and the function that takes the infinitesimal part. And we need to have versions that do that for a function from epsilon to delta, because we are now working on functions, not on dual numbers, but on functions that return dual numbers. So we need to lift these operators and we'll call them beta and gamma. And now below here, you can see that like if I do beta of f compose alpha comma a, that yields f of a. And if I do gamma on the same value, we get the derivative of f applied to a times a. Again, I'm going a little bit fast here, but there's nothing complicated here. It's just purely simple algebraic rules and calculations. Applying this here to the f the triangle f prime, we can write that now as beta triangle gamma of f compose alpha comma a comma 1, and applying that again to our formula. Now we see that there's a little bit more symmetry here because f compose alpha comma 1 appears now on both sides of the equation. And if you squint a little bit at this, it looks already a little bit like an isomorphism because there's the function like, you know, b comma b appears on the as a parameter of alpha, but it's a result on the other side. But it's not yet a complete isomorphism. So we have to do a slightly more surgery on this formula. And what we're going to do is we're going to instantiate a with 0 and then simplify things. And now we get a formula that is exactly an isomorphism. What this says is that alpha and beta triangle gamma are each other's inverses. If you remember the Scholemized version of an isomorphism, this is a perfect instance of that. So what we have proved that we can take our dual numbers property, massage it, and now suddenly we get an isomorphism between this weird function alpha and this kind of, like, you know, this pair of functions beta and gamma, which are really the projections on the dual numbers. And of course, we have not lost anything by taking A equals 0, because from this smaller formulation, by substituting F to be F composed alpha comma 1, we can reproduce our original one. All right, recalculating. What we found is that the pair of values of the pair of real numbers is isomorphic to a function from infinitesimals to dual numbers, or using alphas and betas and gammas, it's the one on the left-hand side. But if we can put the types of alpha and beta triangle gamma, we see the isomorphism very clearly there. So this pair of real numbers is isomorphic to a function from infinitesimals to dual numbers. And what we can do now is we can take this as the axiom. So we take as the axiom that these two functions are isomorphic, and then we define differentiation just as gamma of F composed alpha comma 1. And now there's no intuition required. Probably by now you don't even understand what's going on anymore. It's all just symbols that were pushed around. And that's exactly what I love about this, because there's no intuition about tangent lines or anything. We just defined that these two functions are isomorphic, and then we define the derivative as this weird term here. And from this, all the theory of differentiation follows. And that's the beauty of this thing. So you have one simple axiom, you define differentiation in terms of the functions you defined up there, and everything follows from that, just using pure algebra without any intuition. And that's lovely. Intuition is a bad thing. If you think that you can understand derivatives by looking at tangent lines of graphs, that's fine for 2D graphs, but what if you have dimension of 1,000 or 1,000,000 that you have in neural nets? Now your intuition just evaporates, so you can better start without any intuition. Now we're going to use another trick. Let's revisit here our isomorphism, and we can do three things. We can substitute F on the top into the formula at the bottom. We can substitute the pair B comma B into the formula at the top, and we can use the fact that this thing defines something uniquely. So there's three theorems that we can get out of this for free. So let's look at them one by one. If we substitute the B comma B into the formula on the top, what we get is that F equals alpha beta F comma gamma F. And this is kind of like, it says that any function F can be written using alpha and gamma. If we substitute the other way around, then we can see that the pair B comma B equals this complicated expression here. And again, it shows a little bit here that this pair B comma B can also be written as a function of itself. But it goes the other way around. And that's not surprising because it was an isomorphism, so these formulas should be slightly symmetrical. And then from uniqueness, we get that alpha A comma A equals alpha B comma B if and only if A equals B and A equals B, capital A equals B. And that's exactly our structural equivalence that we had in the beginning. So we get micro-cancellation also for free. So these are the three tasty theorems that we get for free from the formulation of our axiom as an isomorphism. And this is beautiful because now we can really kind of compute what beta is and what gamma is just using these definitions. And we can reconstitute our original definition of dual numbers just using the axioms and these rules. So now the circle is complete. We started with the formulation of dual numbers in variable form. We made it point-free. We defined a new axiom, and now we can show that from that axiom, we can derive our original formulation again. So everything is still consistent. And this is a trick that you can apply in many cases. So if you define your abstraction f using a universal property, so it's like, there's with this uniqueness thing, and for like, there's a unique B such that B A of B. And it could be an isomorphism like here, but it could be something else like we see later. And then we can substitute this formula, the left-hand side and the right-hand side, the right-hand side and the left-hand side. We get all these free theorems, and we know that B is unique, so we get that also for free. And now everything becomes symbol pushing. So if you can axiomatize your abstraction in this way, everything becomes symbol pushing, and that's beautiful. Now, this is not a trick, of course, that I invented. I already said that there's nothing new here. In Squiggle, this was the most widely used trick. If you look in category theory, this is when people say we define things using universal properties. So that's kind of like, another trick. So it's a really kind of like super useful trick that I think deserves more attention. People should use this more also in computer science. All right. Let's now look back at the simplification that we did. So on top here is our fruit fly, and at the bottom is the alpha that was defined by the lover numbers. And what you see here is that, like, in the bottom formulation, there's a recursion. There's r comma r is isomorphic to delta arrow r. This feels a little bit like, a recursive domain equation that's really complicated. And that's why if you have this recursion, you need to drop something. And that's why we have to drop the excluded middle to make this all work. And the top one is a little simpler, so we don't have to drop everything. But as I said, like, dual numbers don't give you everything. And what don't they give you? Well, for example, if we have functions with 2 parameters, now if we look at the derivatives, we get confused because we cannot, from the result, we cannot reconstitute the partial derivatives of the function with respect to one parameter or the other, because we only have like 1 unit of perturbation, but we need 2. So in order to make this work, we need to distinguish between epsilon1 and epsilon2. Now let's kind of like look at Taylor expansion and see, like, why we also need multiple infinitesimals here. So let's look at here. If we want to get, like, have higher derivatives, we need to have multiple units of perturbation, and we need to have recursion. And you can ignore the calculations, just look at the red formula at the top and the yellow formula at the bottom. And what you see is that we need 3, if we want to go up to the third derivatives, we need to have 3 different infinitesimals, 3 different units of perturbation. But what we see is that we get something that looks very much like here, Taylor's rule, where you see the factorial term appearing. And in general, we can prove, and it's a fairly simple induction, that if we have, and if we write the dual number there using inner product, we can write this Taylor formula here. But again, it requires that we have multiple infinitesimals. So dual numbers don't really cut it if you want to have like functions with multiple arguments, or you want to have functions with higher derivatives, if you want to compute higher derivatives. If you want to know more about this stuff, there's a really nice paper by John Bell. It's called An Invitation to Smooth Infinitesimal Analysis. It's a really informal introduction that gives you all the more mathematical details. And then, of course, there's the Bible here from Anders Kok. And John Bell also has his book here, which is a very interesting or nice introduction as well. People have been doing this in the functional programming world. If you want to, as said, like if you want to deal with kind of like higher order derivatives, you need some kind of recursion. If you can read a little bit of Haskell, you see the recursive definition there at the top. Connell Elliott has written a lot of stuff about automatic differentiation, and there also you see a kind of like recursive definition here. It's this kind of like delta star that appears on both sides. So in order to have like a higher order differentiation, you need to have recursion. Dual numbers just don't cut it. And of course, if you want to know anything about automatic differentiation, Perlmutter and Susskind, like read their papers. They are the ones that always kind of find bugs in other people's work when it comes to perturbation confusion. All right, I think I'm at 40 minutes. Let me just take like 1 minute, go 1 minute over time, and then we can go to questions. People traditionally don't like always infinitesimals. A lot of mathematicians don't like them, and it was all caused by Bishop Berkeley, who said like these infinitesimal things are ridiculous. Now, what's nice is that you can also define a different axiom. And again, it's another axiom in this kind of like, universal property style. And using this axiom, you don't need infinitesimals. You can prove the axiom using infinitesimals, so you get a sense that it's true. But again, since it's an axiom, you don't need to prove it. But if you define this equation here, and you define differentiation as the bottom line there, now basically you can find all the theory of derivatives without infinitesimals. And that's pretty beautiful. But the downside of this one is that it's not really leading you to an implementation, where the dual numbers implementation with infinitesimals gives you a very clear way to turn this into an implementation. But this formulation that doesn't use infinitesimals, maybe that appeals to mathematicians that hate infinitesimals. But for us computer scientists, it doesn't really help us because there's no obvious implementation that comes from this formulation. All right, I'm out of time. I promised you to do integration. Well, let me show you the integration axiom. The integration axiom says, for every function there exists a unique primitive such that the derivative of the primitive is a function, and if you apply this primitive to 0 equals 0, we don't need to look at things beyond intervals of 0 to 1, because Hadamard shows how you can extend this. And if you Skolemize it, you get this very simple axiom. And now we can just pull the crank, the same crank that we did in the first half of this talk, and get all the theory we know for integration, just using algebra instead of calculus. So with that, I'll go with questions because I'm 3 minutes over already.
All right, well, thank you, Erik. So now we have questions, which we can have either technical questions or this is an AMA. So Erik has kindly agreed to answer questions. Well, it says you can ask me anything. You have to actually agree to answer them, I guess. Okay, so I am watching the chat in the Zoom, and I am also watching the chat in the in Clouder. So ask away in either of those forums. Philip Schuster asks, are the slides online?
I think the slides are not yet online, but I will definitely publish them. I'm also writing a paper. It originally started as a paper and turned out that once I looked, it was already up to 100 pages. So I don't think I get it published anywhere, but I will kind of like put it up. And also because there's nothing new here, so I'm pretty sure that no conference will accept it. But yeah, I will make the slides available online and also the kind of write-up.
Hi, Erik. Thanks for a great talk. I have a question. So you basically made all these complicated calculus things more a matter of symbol pushing, right? To be implemented in a programming language, for instance. So, but you know, when we use a real programming language, the numbers that we use will probably be floats. Does your, reformulation have anything to say about error propagation and numerical stability and all those things?
So that's a very good question, and it doesn't. And like real numbers are kind of like, really strange things, right? There's like uncountably many real numbers. There's way more real numbers than you can enumerate. Comparing two real numbers is undecidable. It can take, it might not terminate. So yeah, when we implement them in code, we are working with approximations, and then we get all kind of numerical instabilities and crazy things. Right. What is interesting is that if you look at dual numbers, they lead to a lot of numerical instabilities, and people don't often talk about that. Like if you go from like forward AD to backwards AD, you're using associativity. You're kind of like your associativity is going from right associativity to left associativity, or the other way around, which for floating point numbers is not always the same thing. But the funny thing for integration, where that is kind of like numerically more stable. But the implementation is not directly derived from the theory. You have to go, because the axioms, again, don't lead you to an implementation. But yes, okay. It doesn't say anything about that, and you have to be very careful. Now, the other funny thing is that if you look in practice, in deep learning, we are using a lot of functions that are not even continuous. For example, ReLU is a function that has a band. It's not differentiable at that point. It doesn't really matter. People quantize, so they go to get 8-bit floating point numbers, and everything still works. So for the applications where we're using automatic differentiation in deep learning, a lot of these things don't really matter. But of course, if you're sending a rocket to Mars or doing other things, then all the numeric analysis becomes super important. But I think in the deep learning space, we are lucky that these errors don't really matter that much, and we can get along with even coarser approximations.
Okay. Maybe if I may, a follow-up question, because apart from the deep learning world, but in the rocket world, so would your reformulation be transferable to, for instance, using interval arithmetic, where you have explicit, error bounds for, numerical computations? I mean, apart from that being probably not efficient enough, but
Yeah, that one I don't know. I haven't looked at that, but it sounds like an interesting approach. I'm not sure how they kind of like this notion of infinitesimals kind of like would work there.
Right.
But yeah, it's something definitely to look into. Because you probably want to do a differentiation also in domains where numerical precision does play a role.
Right. Yeah. Okay, thank you.
But let me say this, like another thing, like, which is maybe a little bit contradicting with that. There's also a way you can use complex numbers to do automatic differentiation, where you get like a bigger error. It's called complex step differentiation. So if you have a Fortran library that already has complex numbers, you can like, you know, use it to compute derivatives similarly like to automatic differentiation. And people seem to do that. And so, yeah, but you have to be always careful. And that's the kind of thing with floating point numbers. Like, I know that I don't know anything about them. And I don't pretend that I can, like, you know, that I understand all the subtleties about them. I think that's the kind of like safety that you always have to do when you're dealing with floating point numbers. And they're kind of crazy.
Yep. Thank you.
More questions? Either just talk in the Zoom or put your questions on the chat.
I have one question. So you mentioned, Erik, the Connell-Elliott's paper, Beautiful Differentiation. I think it dates back to 2009 or something like that. And just a year or two ago at ICFP, he had, I think, a distinguished paper award for another automatic differentiation paper, Simple Essence of AD or something like that. And so I'm wondering, functional programming communities seem to be attracted by this topic, but I haven't seen yet, you know, a successful example of implementation of this that would be, you know, used somewhere. So people still use this horrible things like TensorFlow, and I hear them complaining about the stateful sort of nature of the whole thing. But so do you have any idea if this is really a good domain for functional programming, like based on your observations and, you know, your experience, or is it a sort of super, like, is it just a way to understand things, but it's not probably like not a good way to implement them, like using the functional programming approach?
So that's a good question. So let me kind of answer that in two ways. The first thing is that if you look at training a neural net, that is inherently an imperative thing, because you're taking a set of weights, and during training, you're updating the weights using backpropagation and driven by the derivative. You're kind of updating those weights to minimize the loss. And then once you've updated the weights, you end up with a pure function. But during training, you're like, the essence there is that you're updating weights. So that's kind of like one thing where, you know, purity doesn't really give you much. If you now have to kind of like formulate this using monads, whatever, like it becomes kind of like pretty complicated, because your normal compositional expressions become kind of like a little bit ugly. The other thing I would say, and this is and my team at Facebook one of my teams at Facebook is working on it. If you look at another advantage that functional programming might give you is typing, right? Like one of the things is that if you look at frameworks like other frameworks, they are kind of like in Python where there's no real typing. But unfortunately, most other type languages also don't have a really great answer for typing multi-dimensional arrays. And most libraries are still kind of like saying it's like a tensor, and they don't talk about like, shapes and dimensions. And this is something where I think the traditional programming language world has let me down, I think, a little bit. And because if you're working with high dimensional arrays at different shapes, and you're multiplying these things, you don't want to get runtime errors. You want to get compile time errors. But if the type system doesn't help you, then you might as well kind of like use Python, where there's a lot of libraries and so on. So there's really not a lot of advantages of using functional and statically typed languages. People are trying to change that. There's Swift for TensorFlow. We're working on a version where we're adding this static typing to Kotlin. But yeah, right now, all these things don't really exist yet. And so I think practitioners just have no choice, and the whole ecosystem and all the kind of like excitement and energy is in Python. And as long as we cannot have something that's really, really much better, I don't think there will be enough pull to move people away from that.
I see. Thank you.
Let's see. Sophia Drosopoulou asks in the chat, higher order functions, do they play any role?
Yes, they do play a role. And now if you want to deal with higher order functions, you get into kind of like, more complicated theory. If you look mathematically, you get into the calculus of variations. People kind of like, deal with higher order functions. There's several papers about that as well, recent papers. But I don't kind of like, touch them here, but absolutely they do play a role. What's also interesting is if you look at higher order functions, it's very, very easy, or maybe not super higher order functions, higher order functions and nested functions. It's very easy to get this perturbation confusion. It's very similar to when people accidentally implement dynamic scoping, and when they implement beta reduction, you get into very similar errors, and where you accidentally don't have the right infinitesimals, and now you're treating something that should be a constant, you treat it as something that's varying, and your whole derivative gets messed up. So yes, higher order functions are important, but they add a lot of complexity. And maybe that's also why a lot of math doesn't, well, I would say maybe, I don't know if that's the cause or effect, but a lot of math doesn't use higher order functions, right? It's like, it's all first order functions. There's functions with multiple parameters, but higher order functions, not so much.
I'll add a little bit to that because I've actually looked into this a bit. And that is, if you look at, hang on, just a second. If you look at the literature of fancy automatic differentiation, those folks tend to want to do differentiation on manifolds. They say that a manifold is a place where you can do calculus. And ordinary manifolds are not closed under function spaces. However, you can construct spaces using these infinitesimals that are closed under function spaces, and it's actually a pretty nice model. It's not half as bad as you might think.
Yep, and again, the book here kind of has a lot of stuff on manifolds as well, but it gets a lot more heavier mathematically, and in all the papers that deal with them, no matter whether you take this approach with infinitesimals or other approaches, it becomes a lot heavier. I think Artem pointed out at a couple of other implementations. Yes, there's the people have been there's a lot of these libraries. It's very much kind of like, you know, in fashion, and people are kind of experimenting with various designs with higher order functions and higher order derivatives. And another thing is like, you know, do you combine like forward AD with backwards AD? People want all combinations in every direction. Yeah.
Do we have any more questions or comments?
Yeah, perhaps I have a question. You got me really excited with this integration thing. Did you find a way to do so an algebraic approach to integration? Do you have any pointers?
Yes, so absolutely. If you look into, let's say, if you look at this book, can you see it? I don't see myself here. Let me just move.
A primer and infinitesimal analysis, second edition, John Bell.
Yes.
And then also Anders Kok has written, like Reis and Kok have written like papers about it. They're kind of like a slightly harder because they're all kind of phrased using category theory. So I showed you the kind of like one axiom for integration. And from that, everything becomes really, again, algebra. The one downside of this, of integration, is that it doesn't really suggest any way to implement integration. So like with dual numbers, you get like, you know, a very straightforward implementation in code of differentiation. For integrals, that doesn't exist. And then you have to do Monte Carlo simulation. So it's kind of like a little bit of a discontinuity there, that the implementation doesn't really follow the axiomatization. But again, like, you know, you can really turn all the kind of like, you know, like everything that you ever did in university with integrals, you can now just do by straightforward symbol pushing. And it's really pretty beautiful, actually.
Thanks.
More questions? If not, let's thank Erik one more time. And
thank you.
we'll see.
Thanks, Erik.
Thank you.
Thanks, everyone. Bye.
Thank you, Erik.
Thank you,
Great
Erik.
talk.
Thank you.
Thank you.
Okay.
Bye.
Bye-bye.
Everyone is encouraged to attend Meet the Speakers after this session.